attention to the cross section. The premises of this is a divergent duct, right? That's why they have the symbology wrong before. Divergent duct. I increase pressure, I decrease or increase temperature and velocity, or decrease velocity. Okay, so there's my divergent duct. Velocity decreases, but it doesn't seem to be as proportional as the way that the pressure is increasing. Okay, we're going to talk about that here later, but this is the reason that the velocity is not dropping off. Okay, the rotating and stationary blades, the rotors and the stators, are increasing pressure. They're divergent, rotating divergent ducts. Okay, but the cross section of this compressor is convergent. The reason being is I don't want a huge velocity drop off. I want to take a certain mass flow and drive it through that engine. I don't want to slow it down. That's what happens when I slow something down. It's just like a brake, right? When the aerodynamics comes, if I throw that thing in there, it's nothing but drag. All of a sudden I have an engine that's nothing but a brake for all this pressure. And pressure's not a bad thing necessarily, but it's not going to efficiently transfer mass flow air through the engine. Okay? So I want to keep it going. I want to keep it the same if possible. So I make the duct kind of convergent, the cross-section convergent, which is going to help even out the actual velocity. Okay, but the pressure head rises quite a bit. Okay, temperature following pressure increases. Okay, in the video they talked about up to 600 psi for the output of the compressor. That is a very, very, very large turbojet aircraft. Okay, pressures for helicopter engines are going to vary between about 100 and 150 psi out of the compressor. Very large turbo shaft engines for helicopters, maybe you'll get a couple hundred psi, but no more than that. 600 psi is nothing you get to see. Okay, so high pressure, temperature's increasing, usually between 5 and 600 degrees Celsius. Okay, axial velocity is around 500 feet per second. Okay, so normally at the outlet of the compressor, if I have a normal flow turbojet like this, I have a diffuser scroll or a transfer tube of some sort that's usually also divergent in nature, giving a little bit of increase in pressure. So when we say, where is the maximum pressure in a gas turbine engine located? It's anywhere from the outlet of the compressor to the inlet input to the combustion chamber. Test questions anywhere, they're not going to give you both. Compressor outlet, combustion chamber inlet. One of them will have compressor outlet, one of them will have combustion chamber inlet. For you, maximum pressure can occur anywhere in there. You can see the way this is drawn, this is actually a little incorrect. This pressure should continue up here just slightly because of the divergent nature of this. So where is the highest pressure? Compressor outlet to combustion chamber inlet. Okay, they're considering this whole thing the combustion chamber, so they just peak it right here. But that's where my highest pressure is. Okay, we need to know where the highest pressure, highest temperature, and highest velocity are in this engine. Okay, so now we hit the combustion chamber. About 75% of the air goes right by it. Right? We're just going to use it to cool the combustion chamber. Okay, this thing is not made out of krypton or something indestructible. We decided it was a high nickel content alloy, right? I think we looked that up before. 2,000 degrees centigrade, or Celsius, excuse me, I like saying centigrade, it sounds more technical. This is about the maximum temperature of this thing. Okay, it would melt. The turbine blades would melt. So what do? 75% of the air-ish, you'll see varying numbers, 60 to 75% of the air goes right around this thing to keep it cool. And we take a sampling of that air, some of it we drive in the front, or snout air, or entry air into the combustion chamber. The rest of it either goes by for cooling or goes through different passages or ports where basically its momentum is stopped and it just turns into a toroidal ring or sort of a rotating static thing. I can't have actual velocity, it'll blow the flame out. Okay, so I want to get this combustion capable gas mixture going on. Okay, so I do that, I light it, I burn it at what air-fuel ratio you think? What's the mixture you think when I light it? 15 to 1 would be great, right? Because kerosene burns pretty much like avgas, around 15 to 1. So 15 to 1 at the flame front. Overall combustion chamber mixtures between 45 and 130 to 1, because we're counting the entire combustion chamber and we have dilution zones and things we'll talk about later. At the point of the flame, 15 to 1, and then it disperses from there. So 2,000 degrees, maximum temperature. Where's my temperature? There's my flame temperature there. They're showing, yeah, just over 2,000, 2,100 degrees at the point of the flame. So, where's the highest temperature in a gas turbine engine? Combustion chamber. Where's the highest pressure? Compressor outlet. Right? You guys gonna remember that? No. Whoever gets the lowest score on the test, whoever misses that question, gets to have them for their bitch for the day. Okay, we'll go high and low bitch. I don't care. Somebody's gonna miss this. Take a break.